Okay, so we're looking at our benzene and reactions with benzene, so substituted benzene reactions, and we're going to be looking at electrophilic and nucleophilic substitutions. Alright, so benzene being an aromatic compound is what's going to drive all those reactions. That high amount of electrons in the from those pi bonds create the reaction center that's going to drive all of our reactions, and it actually creates the entire functional group and all the rules with regard to naming. Now, we see a lot of various compounds with these names, and we see a lot of complex names that pop up. Now, all of these are just ones that are found out in pharmacies for the most part. And but we do see a huge variety in function and use. Now, excuse me, when it comes to nomenclature, we've seen quite a bit of this, and the most complex part of nomenclature on benzene is there's a big use of common names being IUPAC for our common substituents added to a benzene. When it's not so common, there's a relatively straightforward process, which is what we're seeing here: bromobenzene, chlorobenzene, nitrobenzene, and ethylbenzene. When we get to some of the others, we actually end up changing the name to one of our common names that is actually IUPAC. So toluene is when there's a methyl group off of it. Phenol, it's actually OH off there. Aniline is NH2, and benzene sulfonic acid has the SO3H. And now we have anisole with OCl, and styrene with a vinyl group attached, and benzaldehyde, benzoic acid, and carbonitrile. Now, we also have the possibility of these being substituents, the benzene ring that is. And when it is just coming off, we end up seeing called the phenyl group. And in the past, we've even seen us list it as a two-letter abbreviation to save time on writing it. And that is bromobenzene, but it's also phenyl bromide. Phenyl bromide would be more of a common name, though. And you might remember the benzylic position being the carbon that's directly off of benzene. Well, that intact, because of how stable it actually ends, creates the benzyl group. So that does allow us to do ether common names like dibenzyl ether. Alright, when we have our group substituted off of a benzene ring, we typically see the name two different ways. Many ways are going to involve our branch names. So isopropyl, sec-butyl, tert-butyl. There isn't really one for that one, and there isn't really one for that one. But when we have those common branches, we just name what they are and just put the name benzene off of it. When it's not such a common one, we end up seeing in a situation like that, we end up adding the phenyl as a substituent to the long chain. So 2-phenylpentane and 3-phenylpentane. So both happen. Typically with the one that keeps us from having the complex substituent name. And we see this a lot on some of our common names. So the common name here would be phenol, and that's how we end up naming these guys. So by naming it phenol, we define the number one position. So this is 2-bromophenol, and this is 3-ethylphenol. Alright, on to some reactions. So electrophilic aromatic substitution is the first thing that we're going to be looking at here. And what actually happens is an electrophile replaces a hydrogen on the benzene ring. And it is specifically electrophile. It's not a nucleophile. So that's different than what we've seen typically on this. But electrophile, it is something like you know, a Br positive. But as long as it's something we can make electrophilic, we can do electrophilic aromatic substitution. And we're going to see there's a lot of variety here. Most of our reactions in this chapter are electrophilic. All right, now comparing this to alkenes, which seems reasonable since double bonds, we actually see a very different reaction. So just as a review, when we do electrophilic attack on a alkene, we do create a carbocation intermediate, and the nucleophile ends up attacking that carbocation intermediate, and we get our addition reaction across that double bond. On benzene, though, what we see happen instead of that, and getting a di-substituted thing, what the nucleophile mostly does is rip off the H that's on the same location as the electrophile and reform the benzene ring. Which, if you think about it, makes sense, because that would return us back to aromatic compounds. This would be non-aromatic. So it does make sense that that attack would happen that way. And stability is the driving factor. It's a much better product. Okay, so typically here's how we see all these reactions go. We're going to have a slow step where the electrophile gets attacked by the benzene ring, creating a carbocation. Difference being now it's the carbocation is part of that ring. And we will have resonance that will stabilize that. And then we have a very fast step where something comes in, a base or something with a lone pair, and rips off that H and gets us back to the aromatic compound. Okay, now, common reactions we see that electrophilic aromatic substitution are just halogenations. Chlorine and bromine are easily substituted onto our ring, but remember how we wanted these to be electrophilic? Well, chlorine, not really necessarily electrophilic, neither is bromine. So we use Lewis acids, the iron chloride and the iron bromide, to actually weaken this bond. So if I put the FeCl3 here and temporary bond, that will help pull those electrons with it, making that chlorine electrophilic. And that is what we use. Those Lewis acids actually allow this to occur. Our Lewis structure of that temporary thing shows the slight positive here on that bromine, but that helps pull these electrons around. It's going to allow this one to be electrophilic. It's going to allow it to leave as, or behave like a Br positive. Okay, so once we've made that, that complex is what gets attacked by the benzene ring. Same with the bromine with the iron bromide. That's what gets attacked, and we create that intermediate. Now this will resonate. I don't have all the resonance structures here, but like for this one, gonna move this up and put the positive here. And I have another, I'll have to put it up here. We're going to move this up and put the positive there. But those three resonance structures give some stability to this until the base comes in and pulls off that H, leaves us to Cl. Okay. Now, iodine can work a little bit different, though. Rather than try to use a Lewis acid here, we find that we can actually make iodine into a cation by just using an oxidizing agent. And the oxidizing agent of choice is typically just hydrogen peroxide. There's some hydrogen peroxide in there with some acid, and you'll make your iodine into an I+, and then electrophilic substitution will occur. Alright, nitration, putting on NO2, is actually relatively easy. Now, being HNO3, that typically seems like that should create an NO2 positive simply because it's acidic. But H2SO4 is just used to help make it more acidic, because those two react ahead of time, the HNO3 and the H2SO4, to make a nitronium ion. Nitronium ion's not super stable, but it's stable enough that it exists, and the nitronium ion is what attacks or gets attacked by the benzene ring. That's the electrophile. Now, straight sulfuric acid will actually also substitute on there. One H2SO4 attacks the second one to create the sulfonium ion, and the sulfonium ion is what attacks. Now, this typically needs heat because we need that to be extra powerful, so this is concentrated sulfuric acid and heat to get sulfonation to go. There's that. Alright. Now, sulfonic acids get used simply because they are very, very strong acids. And they leave us with nice, big, bulky nucleophilic groups that actually can't do backside attacks to much of anything. So, alright. And it's a reversible process. So if we put the H2SO4 in with some heat and make the sulfonic acid, and then we take that sulfonic acid and just put some standard acid and not so much heat, it will actually pull the SO3 back off. Alright, Friedel-Crafts is the next type of thing we're going to use. It's kind of a coupling reaction, so it's going to give us the ability to put a carbon group onto a benzene ring. But all of these carbon groups will technically have a carbonyl, which is what's going to get attached to the ring. So we've got a carbonyl for chlorine or an anhydride, and we have a Lewis acid in the form of aluminum chloride in there. That Lewis acid helps make this thing into a good leaving group, which leaves a positive on the carbonyl, which is what gets attacked by the benzene ring. We see that here in our mechanism. Aluminum chloride helps rip off the Cl, leaving this carbonyl with a positive charge. And this can be stabilized, but this guy is going to get attacked by the benzene ring, and then we'll have a step where the base comes in and removes the hydrogen, and we've now added the carbonyl and the R. Now, if you try to do this twice, we have a dilemma that the aluminum chloride that was created in that second step will form a complex on the oxygen, and this actually forces that positive V up here, moves it from the carbon to the oxygen itself, and anything else that tries to attack is going to get a dilemma. So we can't really do this twice yet, but we typically have to use, even though the aluminum chloride is an acid catalyst, we typically have to use one whole equivalent at least, just to make sure it happens, because the aluminum chloride will actually get used up as go along and form this complex. Alright, we can do this with very small carbon, so single carbon. But unfortunately, formyl chloride, which is what we have here, is very unstable. So it's this reaction written like it is, while it looks like it's fine, it does look like, well, this would form that positive, which is what gets attacked by that benzene ring. Unfortunately, the formyl chloride is not very easy to make. So to do it, what we're going to use is this Gauter-Montage technique where we take carbon monoxide and HCl and put them under high pressure, forming the formyl chloride. And as long as we have some aluminum chloride in there, or copper chloride, or with copper chloride, we can actually make the benzaldehyde. Alright, Friedel-Crafts can also be used just to put a straight R group on there. Very similar type of look here. Instead of having a carbonyl, it's just the R. The chlorine will get removed and the R will go on. Mechanism is relatively straightforward. The aluminum chloride allows that to leave, leaving a cation. And the cation gets attacked and goes on. But reason we have two different ways of doing this type of reaction is because of that right there. The other one that formed was carbonyl if positive. And if we stop and think, we might imagine there's a problem there, because while that cation is not going to rearrange on us, this one might. And that really is the problem we see. If we actually were to use chlorobutane here, which would create a primary carbocation, that's going to easily do a hydride shift, which is why we'll probably end up getting the sec butyl attached rather than just straight butyl. And that's what we see on the Friedel-Crafts where we just have an RCl. If it's just an R and a Cl, you have to worry about the possibility of that rearranging. And if it rearranges to something that's undesirable, not so good. Alright, so because of that, we have to have a different strategy. We'll come back to this later. So how are we going to guarantee we can make N-butyl benzene? Alright, well, the strategy is almost always the same. We're going to actually, instead of using just a standard R group, we're going to use a carbonyl, put it on without any rearrangements, and then remove the carbonyl. So if I put in, well, this isn't a butyl group, it's a propyl group, but if I put propyl with that chlorine on there, I'm going to get the carbonyl and then the two hydrogens. And then I can use hydrogen with the poison palladium to remove those, remove that oxygen. And we have other ways to actually remove that. Clemenson was one that our book introduces later on, where it's the amalgamated zinc with some HCl, and it will do the same thing. Wolff-Kishner will do the same thing. That was introduced here recently. But multiple different ways. And the advantage here is Clemenson is under acidic conditions. Wolff-Kishner is under base. One of those might not work given what your starting compound is. Now this one's going to be fine with either one of those, but if you had an acid sensitive or a base sensitive starting reagent, you wouldn't want to use either one of these. Like for instance, if I actually had a nitro group on there, and I tried the H2 with the poison palladium, I could indeed get rid of the carbonyl, but it also turned the nitro group into an NH2. Wolff-Kishner actually focuses just on the carbonyl. And I don't have it on here, but there technically was another way of doing the same thing, and that was that Mozingo reaction with SH2, where it made the ring with the S's, and then you just eliminated that. Okay. As a review, we can also have done this with any of our coupling reactions. So using a Suzuki reaction for organoborate, where the straight chain carbon was part of the organoborate. As long as we just halogenate that, we can use our organoborate Suzuki step to put the straight chain on there. We can also do a typical organocupric, a Gilman. Same type of thing. We're going to be able to put a single carbon, so we're going to put that R group on intact without any rearrangements. Alright, as a reminder, when we actually do some of our basic reaction, benzene causes those reactions to be slightly different. For instance, the benzylic position is the most reactive center on a organic molecule if it exists. So if I do bromine with light, I'm going to put a bromine on that location, and only that location. And I can easily do a substitution or an elimination on that. Eliminations are going to be very easy because they form that double bond that's conjugated to the benzene system. That benzylic position will do almost any SN2. Now this top one, we actually also have the possibility or the problem that being that that's an OH. Oh wait, never mind. That doesn't apply here. So that OH will actually do a substitution there. Seeing these are just nucleophilic substitutions. They're going to have no problem on that benzylic position. Now when we do reductions, we saw the hydrogen, poison, palladium. That will actually reduce quite a few of the double and triple bonds available. So styrene can turn into ethyl benzene relatively easy. Nitrile can get turned into a benzyl amine very easily with just hydrogen and rainy nickel. And even the benzene itself can get reduced to cyclohexane. It just takes a lot more temperature and a much higher pressure. All right, our groups can be turned into carboxylic acids with the presence of chromic acid, and that chromic acid, to do this, all it really looks for is those benzylic positions. As long as you have at least an H on there, doesn't matter what else is on there, but if one of those locations is an H, you will actually turn that into a carboxylic acid. However, if there's no H there, on that benzylic position, no H is off the benzylic position, you get no reaction and it stays intact. Alright, nitro reduction can be turned into an aniline, so nitrobenzene to aniline with just hydrogen and poison palladium without too much difficulty. Alright, and one more oxidation that we have. Now, we've actually had this listed before, but it's the allylic oxidation, and it's really where you take a benzylic OH, or where we saw it before was when it was part of a vinyl position. So the OH is a position away from a pi bond. And on both these cases, if we just put it in with some MnO2, we will turn that to an aldehyde. And same thing would have happened here. Alright, nomenclature on disubstituted is actually going to follow the same type of rules we saw with cyclohexane. Now, there is one exception. When we have two of the exact same things, so these are all bromos, we also see letter abbreviations that actually say the same thing, letter or phrases, ortho, meta, and para. Now, ortho is when they're directly next to each other. Meta is when there's one empty between them, so 1, 2, 3, and directly across from each other is para. So while it is proper to say 1,2-dibromo, 1,3-dibromo, and 1,4-dibromo, it is also perfectly acceptable to say ortho-dibromobenzene. Now, weird thing is, your book shows these in red, but technically speaking, those are IUPAC approved. They're just a little bit less common now than they used to be. The numbers are far more common now. And another interesting, even though these look like they're the same thing, we got metas and paras, we don't typically see meta and para used when they're two different groups attached to the benzene ring. So since this is a chloro and an iodine, the 1-chloro-3-iodo is a much better name, and I'd be actually saying that that's not really seen ever. Oh, that one's definitely not. But the metas, orthos, and pairs are not really used when there's two different groups. Yet we are deciding this based on alphabetical order. We have a chlorine and an iodo, so chlorine goes first, it gets the number 1. Bromine and nitro, bromine goes first, so it gets the number 1. Chloro and ethyl, chlorine comes first, so it gets the 1, and that's the 4. Now, there are going to be the times when our common names pop in. So like the COH is benzaldehyde, and benzaldehyde makes that name simpler, so we're going to put that there, and that means we have a 2-chlorobenzaldehyde. Aniline with the NH3, so a 4-nitroaniline. Phenol, 2-ethyl phenol. And weird thing is, we could say toluene, but there is actually no such thing as 3-bromo-toluene. Toluene is only used as a name when the only thing on that ring is a CH3. Now, odd thing about this, methylbenzene is allowed to be used as a backbone name, and it implies the 1. So while this shows 3-bromo-1-methylbenzene, you also see this called 3-bromo-methylbenzene without a number. All right. Now, there are some disubstituted names that get their own common name. So having a CH3 and an NH2 is what you have in toluidine. 2 methyl groups are xylene, and CH3 and an OH is creosol. And there we do use those simple abbreviations, ortho, meta, and para, to distinguish these, because, for instance, there is a paraxylene, and it looks very much like this, but the CH3s are opposite. Once we get up to poly, just follow the rules like our cyclohexane. Find the shortest path between the substituents, and then list them alphabetical order. If one of those can give us a better common name, like this first one's going to give us benzoic acid, we're putting that at the number 1 position. Phenol, 1 position. Aniline, 1 position. And everything else is numbered based on that. Take the shortest possible route. All right, now we have some interesting conflicts going on. Turns out all those simple electrophilic aromatic substitutions we introduced will actually change the reactive nature of the ring. What I mean by that, standard benzene is going to be nucleophilic enough that it actually drives a lot of these reactions with the electrophilic aromatic substitution. However, we do have groups that we could attach to the ring that would actually donate electrons into the ring. Anything with, like, say, I'll put it here and attach it, with a lone pair of electrons directly on it, those electrons could get donated into the ring. That makes that ring more nucleophilic, and it speeds up the reaction. And if there are groups that donate, there are also groups that withdraw, which would do the exact opposite. Now, what we're going to see is we're going to end up calling these activators, and these are deactivators. Now, activators and deactivators really apply to the electrophilic aromatic substitution. What we're seeing is there are going to be things that we can add to the ring that will speed up the reaction, and there are things we can add to the ring that will slow it down. A great example of a donating group is something like what we see in anisole. So what happens is the oxygens lone pairs get donated into that bond, creating a double bond. But when that happens, it forces a negative charge into the ring, which will resonate around. But that resonance has made this ring slightly more negative for that time being. And negative nucleophilic has going to greatly enhance the electrophilic aromatic substitution reactions. A nitro group does the exact opposite. The nitro group on a nitrobenzene actually ends up starting out with a positive charge. There's a minus on the oxygen, with a little bit of resonance going between these two. But what we're going to see happens here is we pull these electrons up here, make both these oxygens negative, which pulls an electron from the ring and makes a double bond to that nitrogen. So the nitrogen still has 4 bonds. But by doing that, it pulled those electrons away, forced a cation onto a ring. The ring will stabilize it by moving it around to those 3 locations, but we've essentially removed electrons from the ring. We've made the ring less nucleophilic. Alright, so what does that do? There's a few things that our strong activators do. The lone pair in there will actually donate electrons just by resonance. That's what we were seeing before. That's where the electrons drop in there and force that negative to move around in the ring. Now, all of these do slightly withdraw electrons because the nitrogen or the oxygen is more electronegative, but that's actually not very significant compared to the resonance. The resonance is actually what's going to create more electron density in the ring. Moderate activators have a very similar structure. They typically have an O or an N, but on the opposite side of the benzene ring is something that's helping to withdraw the electrons. So like a carbonyl. So the nitrogen is going to be, yes, donating rings into the donating electrons into the rings through resonance, but it's also going to be donating them to this oxygen through resonance. Let me move that here and up. So that competition is going to not make this ring nearly as nucleophilic. Same thing happens with an oxygen if we put a carbonyl. We can move these electrons here and up rather than into the ring. And so the resonance is helping to take electrons away from the ring. And there's the full draw up of all the possible ways that those electrons could move on that second one. And this step here is the new one. Alright, weakly activating groups actually just kind of donate electrons by the fact that they have extra electrons or hyperconjugation. But that donating makes them all slight activators. Okay, now our weakly deactivating groups are our halogens. Now this is because while they do donate, and they do donate through resonance, the amount that they donate through resonance is not nearly as high. And that really has a lot to do with the fact that if this were to donate into that, it's forming a double bond, which is what would happen with all these. And that's just simply not as stable off of a halogen. Halogens don't necessarily like to do that. So that resonance structure is not nearly as stable as it was. So now we have to focus on the fact that the halogens are just a little bit more electron withdrawing. That withdrawing effect makes them more deactivators. Alright, moderate deactivators are going to have those carbonyls we saw before on the moderate activators, but on the deactivators we put the carbonyl directly off the ring. What that does is that slight positive nature to this pulls the electrons into it. We're going to see withdrawing via resonance because this could move here and that could move up, making positive and a negative ion, but it does actually cause resonance to make this ring electrophilic or more electrophilic. And the withdrawing is just because that is a polar location pulling the electrons towards it. But both those, the withdrawing and the withdrawing from induction and from resonance, actually both contribute to the fact that this will be less nucleophilic of a ring. And our strong deactivators are really things that actually take that to another step. So nitrogen could be a positively charged center by adding those nitro group, these oxygens for the nitro group, or by turning it into a quaternary location. And both of those would actually withdraw electrons tremendously, make it very electrophilic. And we see the same thing happen with sulfur, pulls it very withdrawing, and even nitrile. A little bit more so than a carbonyl, so it's actually a lot stronger of a deactivator. Now, our book actually compiles them once we make them, and we have our whole list of all of our activators and deactivators. And that's what we've listed right here. We're going to see what this column is here in just a second. But we have a very common thing up here. These guys all have a lone pair directly on the atom that's able to donate in. Our moderate activators have that lone pair. But on the side other than the benzene, you have a carbonyl. Then you have just your carbons, your R groups. And then you have hydrogen, the base standard, so just benzene. Then you have your halogens. And then you have all the carbonyl containing compounds. And then you have the ones that are a lot more noticeably positive on that atoms connected to the benzene. Alright, why did we learn all this? Well, it turns out having activators on a ring will speed up a reaction. So, starting with toluene, and rather than benzene, we would see the electrophilic aromatic substitution of bromine will be easier. However, we will actually see the bromine only goes to two locations often. We don't ever see any bromine in that meta position. It's always ortho and para. Alright, the reason that is, we can actually see what's going on if we look at our resonance structures. When we actually have that attack in the ortho position, so it goes on right there, that causes this double bond to move up, creating a cation. This will move around, create another cation. This will move around, create another cation. But this guy right here is a heck of a lot more stable because it's actually a tertiary cation. We see something similar if our attack is para. So we're going to come down here. So we make a cation at the 1 position, or we move it down, it's at 3 position, and we move it around, there's a 5 position. It's always going to be every other location. But here we get a very stable tertiary carbocation as well. But if we attack the meta position, which is available, we have a cation there, which will move up to here, which will move up to here, but we never get that tertiary carbocation. And simply because of that, the carbon, that toluene is never able to stabilize it. But since the attack could happen anywhere, we find it more favorable to attack ortho and para. And we will see that we consider all of our activators ortho-para directors. And that's what that's the case. If you have an activator on a ring, our ortho and para locations are where the substitutions are going to occur. It's a lot more obvious, or it's a lot stronger of a preference if we have a strong activator, because the strong activator adds another layer on it. So think about this one, having that positive right there where the oxygen is. Well, the oxygen is just going to drop a pair of electrons in there and move the positive up to the oxygen itself. Gives a much more stable intermediate, but that leads to a much more strong affinity to ortho and para attacks, because you get this very strict, very stable intermediate. Alright, because the strong activators give us that extra stable intermediate, we will see that we don't always need all the actually same ingredients. That's in the wrong location. It's supposed to be right there. No. Where is it? Right here. So our strong activators get us so we don't necessarily need our iron bromide. Now, we would need, if we need to do it more, so if we want to put 3 different bromo groups on there, if we want to occupy all of our ortho pair positions, we need the iron bromide. But those strong activators, because of this additional complex, allow that to happen without having the hydrogens in there. All right. Halogens were introduced before, and we pointed out that they were deactivators, so they make this reaction harder. But we do see that they are ortho-meta or ortho-para directors. So even though they make this reaction slower, we finally do see the halogen goes on the ortho-para position. And it's mainly for the exact same reason. The additional complex where that positive was created right on top of the bromine can actually move down there and move that positive up. And that stability helps that occur. So ortho-para gets to be our attack site. All right, all of our deactivators are actually going to primarily go into the meta position. Now, the reason is very similar, but it's not based on stability. It turns out having that positive location and attacking ortho-para position, ortho or para to it, create this little complex issue where we have a cation right next to that positively charged electrophilic location, and having them go right next to each other make a very unstable intermediate, and that would happen anytime we have ortho-para. Yet if you attack in the meta position, that positive avoids that location. All right, we do see that this type of concept affects pHs and pKa's of our acidic functional groups. So phenol and carboxylic acid are both acidic. All right, but in those, off of that ring, if we put electron donating or electron withdrawing groups on there, we will affect the pKa. Electron withdrawing groups pull those electrons away, which allows that to come off easier. We will see that increases the pKa of both these groups. So we have a very similar trend that a nitro, a very withdrawing group, will actually withdraw a lot, making a very low pKa, and a donating group like the anosol will actually make it much, much higher. And forget that. All right, so ortho-para ratios, we typically expect about a 33% chance to all of those positions. So 33% chance it's here, 33 it's here, and 33 it's down there. But since these two lead to the same product, technically, we see that most of the time. All right, there is plenty of reasons to expect it to be lower. The reason this isn't 66% is because nitro groups are kind of bulky, and that CH3 is already there, so they really can't get that perfect ratio simply because of that. It's actually bad enough that if I use a much, much bigger group, even ethyl is big enough, that I tremendously lower that. So if I go up to tert-butyl and attached, we will see that there's almost none of the ortho. It's almost all going to go para. And that really is the driving factor. When there's two different groups on there, when there's a group already on there and you're attacking ortho-para, the bulkier or bigger that group is, the more of an effect that's going to be. Yeah, we saw that. All right. Friedel-Crafts needs to be modified as well, because it turns out I can't put an R group on a ring with a deactivator. So if I try to put this in there with my aluminum chloride, but I have a deactivator on the ring, I get nothing. And another weird one, you see this type of thing pops up quite a bit with aniline. Aniline actually is a difficult one to work with because that lone pair is a reaction center. And if I put aniline with aluminum chloride, Now the plan is to put some RCl in there and attach an R group in the ortho or para position. We can't do that because the aluminum chloride actually neutralizes that aniline base, and this becomes a meta-director. And it's also deactivated enough that the RCl, even if it is electrophile, will not attack that ring. It's too deactivated. What we're going to do in that case is protect ourselves by taking that aniline and turn it into a weak activator by just doing making an amide. This is a technique we would have seen in a few chapters ago. The amide, still an activator because that nitrogen still has a lone pair, but it's not going to get neutralized by that, so we can do a lot more with it. And it's a reversible process. Now this isn't really an R group, it was a nitro group, but if I had actually tried to do HNO3 with H2SO4 straight to aniline, the aniline would have been turned into NH3 positive, which is meta-director, and the only place our nitro group could have went then is meta. So if I want to leave this as an activator, this amide technique is going to do that. Excuse me. All right, so that introduces the concept that when we actually want to put two different groups on there, the order which we put them in is very important. So if I want to sulfonate and brominate, I have to be careful of how I do that, because if I do sulfonation first and then bromine first, since SO3H is a meta-director, we will get just one product. Meta-bromo, or 3-bromobenzene sulfonic acid. But if I reverse the order, put bromine on there first, since bromine is an ortho-para director, we get both the ortho and para version of that same bromobenzene sulfonic acid. Alright, but when we're doing our retrosynthesis, we'll have to take that in consideration, so we plan our products accordingly. Alright, other things about the order. Sometimes you can't switch them, because if I try to switch these two and put the nitro group on there first, I would have had to put a deactivator on there, and I cannot put this on if my ring is deactivated. So I'd have to do that Friedel-Crafts first. Now, something else that pops in. So if we actually start with a toluene and do our chlorination on it, we're going to get ortho and para. And then if we do the chromic acid, we're going to turn that to carboxylic acid. But if we had done the carboxylic acid first and made the benzoic acid first, and then did our chlorine, we see that the CO there makes us a deactivator, and we get the chlorine in the meta position. Alright, so when we actually do synthesis, it's very important to actually plan out how we want to do it. So if I do want to make m-dipropylbenzene, two different R groups off of a benzene, I don't want to just put one on and then attach the other, because a straight R group is an ortho-para director. So I want these on in the meta position. Alright, well that's fine, because if you think about this, I do want those to go on as carbonyls. Because if I just try to do RCl, these guys would rearrange and we'd have isopropyl groups attached. So that is going to be my first step. I'm going to take those 3 carbons, but the last one is carbonyl chloride with aluminum chloride, followed up by water, and I will get a single carbonyl CH2CH2 attached. Alright, now that's deactivated, so I can't do another Friedel-Crafts. But I could do bromination. I know that doesn't seem like a very good idea because bromine is not an R group, But what I was going to suggest is after we do this, we could just do an organoborate, replace bromine, do a Suzuki, or we could actually have done a Gilman, but we can replace that bromine with an R group of our choosing from any of our coupling reactions from, I think it's chapter 10. So yeah, we'd brominate it, then we'd actually get rid of that carbonyl, and then we can use our organoborate to put that group on there. All right. So preparing propylbenzene sulfonic acid and para. So I'm going to have the propyl group and then the benzene. Yeah, I've got a couple ways we could do this. So we're going to do that same type of thing. So since this is CH2, 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 and I want to put it on without any rearrangements, I can put it on part of a Friedel-Crafts, but have it as a carbonyl. Then I could use any number of things to get rid of that carbonyl. And since that is an ortho-para director and it is bulky, if I put that with some H2SO4, I would expect primarily the para position as the attack. And down below they have us doing a coupling reaction where we put bromine on there and then do a Suzuki to put the CH2, CH2, CH3 on there, and then do the same final step. Alright, tri-substitute is a little bit easier to make a call because there are going to be fewer choices in many cases. There's going to be fewer ortho-paras available on our disubstituted. Alright, but on this particular thing, since I have a methyl and a nitro, we're actually going to see our attack centers are ortho to just the methyl because it's a activator. The nitro is a deactivator. It doesn't call the shots. So when I do nitration of that, I would get nitration ortho to the methyl. Similar thing pops up here. The methyl is the strongest activator, so we're going to have ortho and para to it. But the one ortho, being between both these guys, can be a lot harder to get to, so we're not going to see too much happen there. So we're going to have two products based on those two locations. Now here's a situation where we have two different activators. The CH3 wants to activate these positions, and of course where the OH is, and the OH wants to attack these positions and where the CH3 is. Well, it turns out OH, being a strong activator, is going to actually call all the shots. So bromination is going to occur at those locations. Now when they do have ties, and it does happen, so methyl and an ethyl group, neither one of them necessarily activate more than the other. So both of those are ortho directions to the ortho substitutions to their locations. And you end up seeing both those products. Now, I didn't see both orthos to the methyl because they're technically the same. And same with the nitro group on the other one, the ethyl. Alright, next little functional group we have to deal with gives us a lot of versatility. It's the diazonium salts. Now, we can make these easy enough from aniline. And we just have to put in some sodium nitrite along with some HCl, keep it cold, and you get this nitrogen-nitrogen triple bond attached. Well, where this comes in really nice and handy is almost any nucleophile can come in there and replace it. Now, we're going to see that there is some limitations to how we do this to get the reactions thing. So it's not really safe to say all nucleophiles, but there's quite a few that actually work quite well. Oh, there's making it. So sodium nitrite, HCl, and 0. You can't store it, so it's not like we can buy the diazonium salts. So you have to make it. But sodium nitrite's easy enough to keep around. Now, once we've made the diazonium salts, and we can make them from any aniline, so if we can make the aniline, doesn't matter what other groups are on there. But all of the nucleophiles we're going to see here typically have copper 1 in common. So copper 1 bromide, copper 1 chloride, copper 1 nitrile. And what's attached to the copper is what gets attached to the ring where that diazonium salt was. There are some others that pop in, but you'll almost always see these copper 1s as the key. So, if we'd actually started with methyl, which is an ortho para director, and put some chlorine in there, we'd get ortho and para. However, had we started with an aniline and added the ethyl group on there, because of the bulk, we'd end up with almost nothing but para. And then sodium nitrate would turn that into a diazonium salt, and then copper 1 chloride would turn that into a chlorine. So we see that we can get better yields by utilizing this technique. Alright, and we can use this to add fluorine and iodine, which we couldn't on, we can't do with F2. We can do I2, but this is the only way we can put fluorine onto a aromatic ring. So we have our diazonium salt, and potassium iodide would put iodine on there. Got our diazonium salt, and HbF4 puts the fluorine on there. Alright, it's also about the only way right now we can make phenol. And all we do there is have our diazonium salt, add strong H3O, any acid, and you make phenol. We can do the same thing with copper 1 oxide and actually get slightly better yields. So copper 1 oxide with copper nitrate and water does the same type of thing. And we can put hydrogen on there. This is a pretty neat reaction. We've got aniline, and we're going to do 3 bromines with iron bromide and put them in all those ortho para positions. Then the sodium nitrite would turn that aniline into the diazonium salt, and then H3PO2 turns the diazonium salt into just an H. And this really is one of the few ways we can do something like a 1,3,5 with activators. Because if we try to do that with just a bromine 3 times, the first one would go on, and now it's an ortho para director. That's about all we get. But if I want 1,3,5, I need something else calling the shots. And this is a great way to put on a strong activator and then remove it. Alright, so retrosynthesis. Let's say we wanted to make m-dibromobenzene. Now those are both ortho para directors, but what if one of them was put on there with copper bromide, so it was a diazonium salt? Well, that is a deactivator. This really shouldn't be NO2. That was made from NH2. But I can make NH2 from NO2. NO2 is a deactivator. So that's what we see we end up doing. We take benzene, we put a nitro group on it, it's a deactivator. So when we put the bromine on, it goes in the meta position. Now we have these 2 steps that would turn a nitro group into a diazonium salt. So hydrogen with poison palladium followed by the sodium nitrite. We have a diazonium salt. And then just copper 1 bromide. You put a bromine on in that location. Alright, another thing that we can do with these, it turns out if our diazonium salt is reacted with phenol, or any of our strongly activated rings, that ring itself will attach to the outermost nitrogen and make an azo compound. Azo compounds are just aromatic with a nitrogen-nitrogen double bond between the 2. Very big pi system. We see these are actually used as dyes. Here's the page I wanted to. So azo compounds are dyes. They're used for clothing dyes a lot. because they bond directly to the cotton fibers, so you don't get color fade with each washings. Alright, but mechanism is relatively straightforward. You have your strong activating ring attacking the backside of that nitrogen-nitrogen double bond, or triple bond, creating electrophilic aromatic substitution, which just goes on and removes that H. So it is standard just electrophilic aromatic substitution. It's just that this strong activator attacks that electrophilic nitrogen. Alright, now on to our last little class of reactions. It's nucleophilic aromatic substitution. And as you might imagine, we're going to put a nucleophile onto the ring. Now, all of these that we do easily are going to replace a halogen. So this halogen is going to get substituted with a nucleophile. And this is a very nice one. Just water at 40 degrees Celsius followed up with HCl would actually turn that Cl into an OH. Now, that won't happen to any chlorobenzene. This particular one works because of all these nitro groups. Alright, the mechanism here we're going to see is an addition-elimination. So that's going to explain why these nitro groups are needed. Because it turns out if I remove them, water alone is not strong enough. So if I only have one nitro group on there, I actually need to put OH in there. It has to be very, very high on pH to get that same type of product. Now, if I have two nitro groups on there, I don't need it quite as basic, but I still can't do it with just water. So what we're seeing here is something with regard to this substitution reaction. Those nitro groups are helping it. Now, if we think about it, nitro groups are withdrawing, and that's probably a big, huge factor. Because if they're withdrawing, that's going to allow, or that's going to increase the attraction by a nucleophile. And that is a big thing that's going on. The nucleophile gets attracted to that ring a lot easier with all those electron withdrawing groups. But that doesn't necessarily explain why we need a stronger nucleophile. Not completely. Alright, but the mechanism does. When we actually have that nucleophile come in and attack, we form the same type of complex that we did before, but instead of a positive cation, it's now an anion. And it moves to those ortho positions and the para position while keeping that negative on that ring. But when we have a deactivator in that ortho or para position, deactivator having that positive charge, that's going to pull that charge out onto our deactivator. And that helps stabilize that ring some more. So the more interesting statement isn't not just that we want deactivators on there. We really want them in the ortho and para positions, because that's going to create that complex where the negative gets pulled onto the deactivator. But we're going to see that as long as we have a deactivator in the ortho-para position, we have a lot of possibilities with nucleophiles. Almost any nucleophile will work. So it doesn't need to be just OH. OCH3 will also do nucleophilic substitution. And a big, even bulky one, that nitrogen, is nucleophilic. So it will also do nucleophilic substitution. So as long as you have a deactivator in the ortho-para position, you can do nucleophilic substitution to any halogen. Alright, the last one is a very specialized case. We don't necessarily need any electron withdrawing groups for this to occur. Alright, what I mean by that, we will always be able to replace a halogen with an NH2 if we use sodium amide with some liquid ammonia. However, that replacement will not always be guaranteed where it is. So bromine is, if that's what we want to replace, this technique is going to replace it, but it's also going to put the same nucleophile in an adjacent location. Now this one only creates two products, but if I had actually used bromine and had that CH3 over there, I would have ended up with 3 products. because I could have put that NH2 there. I could have done this, or I move it over. But we also have, I'll put it over here because that's kind of where it fits. That NH2 could have been here. So it's going to be exactly where the bromine is in one of these adjacent positions. Alright, the reason that happens can be viewed with the mechanism itself. The NH2 doesn't actually do a direct attack and create that same type of complex. What it does is it pulls off an adjacent hydrogen. That adjacent hydrogen allows that bromine to get kicked off, and we kind of create a structure with a triple bond. The benzene. The benzene then gets attacked by another NH2, and that NH2 could attack on either side of that triple bond. And then the ammonia in there is what creates the proton that goes back on there. But that gives that possibility that NH2 to be in two different locations. Alright, now the benzene mechanism, while it's very well understood, very limited in application, it really is a bit too chaotic, so it's best to try to avoid that with our retrosynthesis techniques. But it's doable, it's easy to avoid it, and that finishes up with this chapter.